Good day everyone and welcome to Module 2 on the high voltage and safety course. Today we will be focusing on the safety fundamentals and identifying and managing all the risks that are associated with the batteries and with the high voltage systems. This is the agenda of this module, and here we will present and we will be exploring the different hazards that EVs may have, also their effects and the preventive measurements that ensures the safety in the electric vehicles and in the energy systems. We will focus on the electrical hazards, the thermal and mechanical hazards, chemical hazards, and at the end we will provide an introduction of some of the risks that are particular for the battery production. So let's start with an introduction for this topic. And here in this initial slide, we are highlighting both of the negative concerns and the positive developments that are shown around the battery technology and safety. Here we can see some interesting headlines regarding the risk of lithium-ion battery fires, as well as, for instance, problematics of EVs exploding and the fires on electric vehicles. All of these emphasize concerns over fire risk and thermal runaway incidents that of course are causing hesitation around the customers and also on the industry, and all of this is adding relevance to safety measurements in the electrical vehicles design, but also in the industry in general. On top of that, there are also some positive news that highlights advancements in the technology and that states safety standards that are improving consumers' confidence. For instance, we have developments like solid-state batteries that are overcoming several of the issues of traditional lithium-ion batteries. To understand better and to clarify maybe of the terms that we will be using later on, in these slides we will define three of the main terms that we will be using: hazard, risk, and severity. These are going to be fundamental for understanding safety in high voltage systems. So let's start with the hazard, and hazard basically is anything with a potential cause of harming. For example, the high voltage system and the high voltage battery itself is a hazard because it holds a significant amount of energy. On the other side, we have the risk, and when we define the risk, we include one additional component, that is the probability or the chance that a given hazard will harm someone and that at the end will affect a person. It depends on the situation at the end. So a worker could be shocked if the circuit or the battery terminals or the wires are exposed, and the likelihood increases without, for instance, having proper safeguards and proper safety equipment. On the other side, we have the severity, and the severity will measure how serious the harm could be, and this ranges from minor injuries to, for instance, even lethal situations. A worker, in this case, for instance, if it gets into a problem with a low voltage system, he might have some discomfort, and it means that the severity will be low. However, if it gets in contact with a high voltage, that could result even in the death of that person. So understanding these three terms help us to prioritize the safety measures. And for example, in high voltage systems and in EV, the hazards are there. We cannot avoid them, but the risk and the severity can be controlled with proper design, with proper training, and the preventive measurements that we will discuss in this module. Let's take a look at the main categories of hazards that are going to be associated with the high voltage systems and with the batteries. Each of these categories present unique challenges that require specific safety measurements. First of all, we have the electrical hazards that occurs at the end when electricity interacts with the systems or with people in an unintended way. This can cause, for instance, the electric shock. It can produce arcing, it can produce short circuits, insulation failures, and so on. And one example of this hazard is, for instance, touching an insulated wire that could lead to an electric shock in a person. Then we have the thermal and the mechanical hazards, and these basically involve the heat or the physical forces that will damage the battery or the systems in general. So in this type of hazards, we can imagine, for instance, the battery in a crash and the physical impact that could at the end deform and affect the cells, potentially causing a fire. We can imagine that battery, because of the shock, is overheated, and at the end it will cause a thermal runaway. And finally, we have the chemical hazards, and these ones arise from the materials that are used in the batteries. So they can harm the people, and also they can harm the environment. For example, if we have a leakage in a battery pack, that could release toxic gases, and that pose serious health risk for the people that is around that battery. We will dive into each of those types of hazards, and we will start then focusing on the electrical hazards. That is one of the most relevant for the high voltage systems and for the electric vehicles. So let's start establish a definition of what high voltage is. And as you can see here, different organizations and different standards define high voltage ranges differently. Each standard, in this case, each standard will tailor its definitions to the specific risk and the specific applications that the standard is made for. Particularly in the automotive and in the electric vehicles, as you can see, we focus on lower thresholds because even with few volts, we can pose a significant shock hazard in the maintenance or in automotive accidents. So if you can see in the other standards and industries, high voltage is defined above few kilovolts. However, in the automotive, only above 30 volts, we are already talking about high voltage. So according to these standards, we will define high voltage, and you will see that the ranges changes depending on the type of the current. So in the case of DC current or direct current, the threshold is around 60 volts, and this will be the voltage that we use to mark the boundary between low voltage and high voltage and high voltage vehicles. And then if you look at AC, in this case, the threshold is marked at around 30 volts, and this is because of the alternating current nature. So as you can see, it is significantly different. And let's move to a critical topic in the high voltage safety, that is the insulation failure. If we have a proper insulation, the high voltage is not a risk. The risk is very low. However, these type of failures pose a significant risk in our systems. Insulation failures will occur when the material that is designed to prevent electrically the current from escaping from their intended circuits become damaged or it becomes degraded, and this can expose the live components and the conductors, creating a direct pathway to flow to unintended areas, for instance, including to flow through the human body. Some of the risks that are associated with the insulation failures are, for instance, the electric shock, the arcing, the the short circuits, all of these will be explained in detail in the next slides. However, here I want to say and to explain maybe how insulation is the first line of defense against any electrical hazard. Regular testing and maintenance of the insulation, it is essential to prevent those failures and to ensure that we are working in a safe environment. So in order to prevent insulation, we have some recommendation. The first one is always to check if the systems that we are working are having any visible damage, cracks, or sign of wear in the components. Also, we have to keep the equipment and the system dry and protected from extreme environmental conditions. And we also have to work with isolated tools and protected materials. But on top of that, we have the insulation integrity verification. That is something that happens during the assembly process of the battery, but also applies in general when we are operating or when we want to operate with these systems. Basically, this test measured the insulation resistance at the high voltage battery pack, and by measuring that resistance, we can define if there is a good or a bad insulation in our system. How we can do that? So basically, it is a 4-step process. In the first step, we will connect our resistance tester to the chassis, or between the chassis and the negative terminal of our battery pack. Then we will apply a voltage between the chassis and the negative terminal of the battery. This is a high voltage because we will use it then to measure the resistance of the equivalent resistance between the chassis and the battery. And here, after we apply that voltage, we have to wait approximately 1 minute to have a stable resistance measurement. We take out that value, and if the value is above 2 mega ohms, it means that the system is well insulated. This is a test that we can use to validate the insulation in the battery, and also when the battery is being produced, but also if we want, for instance, to disassemble or to work with the battery, we can follow the same process. As was mentioned before, there are different types of electrical hazards that are going to be commonly encountered in high voltage systems, and understanding each of these will help us to better prepare and to mitigate their effects. We have electric shocks, we have arc flash, fire, and short circuit. We will define each of those separately, starting by the electric shock. So electric shock is one of the most common and also one of the most dangerous electrical hazards, and this basically happens when there is an electrical current that passes through the human body. And the severity of this will depend on several factors. It will depend on the amount of currents that will pass through our body, the voltage, and the path that that current will take through our body, as well as how long the exposure lasts. The current and the intensity of the current is what matters the most. Even if we have small amounts of currents can cause serious harm. Here we have maybe different thresholds and what is the effect of those thresholds in our body. So when we have very low currents, maybe below 2 milliamps, in that case we just feel some tingling in our hands or depending on the part of the body that is touching the conductor and the loop of the current, how it is going through our body. But at very low currents, we will just have the tingling that most likely most of us have already felt before. Then if we increase a little bit the current, if we go from 10 to 30 milliamps, for instance, our muscles start to contract strongly, and One of the dangers of that is that, for instance, if our hand muscles contract, maybe they get close, and because of that, we cannot let go the source of the current. If, for instance, there is I'm touching a contactor and my hand closes, I will not be able to release, and the duration of the exposure will be longer, meaning that the effects of that will be also longer. And if we go further than that, if we go beyond the 50 milliamps, the shock can be severe and potentially even causing cardiac arrest or even the death. So besides of that, besides of the intensity of the current, the danger of the electric shock also depends on how the electricity will flow through the body. For example, if, and here we have a human body showing it, but for example, if the current passes from one hand to another, so if it has this direction, as you see, as I'm highlighting here, it will go directly through the heart. So, and this means that it's gonna be way more dangerous than if, for instance, the current goes from the hand to one of our feet and doesn't go through the heart directly. Also, in addition to that, another important factor is going to be the resistance of our body. And that is going to depend also if we are having dry skin or wet skin. If, for instance, we are having dry skin, this is going to be preferable because it will offer more protection because our body will have a higher resistance. But on the other side, if we have wet skins, the resistance will drop, and this means that with wet skin, we will allow more flow of current through our body, and it will mean that we will increase the severity of the injury that we might have. And finally, the other important aspect is the duration of the exposure, and this plays a critical role there, because the longer the current flows through our body, the greater the damage will be. Even a brief contact with high voltage can be catastrophic, or a low voltage during a long period can also be catastrophic. So a combination of all of these factors will affect us. Maybe at this point, let me give you a practical example to illustrate all of that. And here I have made some quick calculation of it. So let's imagine that you accidentally touch a 110 volts lifeline, that maybe it is like the voltage that is in the socket of one of your house. And if in this case your skin is dry, you might only experience a mild discomfort because the current is going to be low. You will have a current of, when we calculate it, assuming a human resistance of 100 kiloamps, we will have a current of less than 2 milliamps, so we will have just some discomfort, nothing too serious. But if we do exactly the same, and we are coming out of the shower and our skin is wet, the same voltage could send a way much higher current, maybe above 110 milliamps, and this can even cause severe, this can even cause to stop your heart, for instance, and to kill you. So electric shock is a severe harm that we have to pay attention when working with high voltage system, but in general with working with electrical systems. Another serious electrical hazard is the arc flash. And when we talk about the arc flash, we are referring to the sudden release of energy that is caused by an electrical fault. Essentially, when the electricity jumps through the air between two conductors, it will create an intense burst of heat and also an intense burst of light. And that energy release can be very, very harmful because, for instance, the temperatures during the arc flash can reach up to, I don't know, 10,000 degrees Celsius, and that is even hotter than the surface of the sun, for instance. So it is very, intense. Even if it lasts few seconds, it is very, very intense. But and maybe just to put it that way, even if it is just for a few seconds, the consequences can also last for your entire life. If we think of an arc flash, we can relate that, for instance, with having a lighting, the strike of a lighting in a very confined space. It is very powerful, it is sudden, and it is incredible how dangerous it can be. To prevent the arc flash, we will define these arc flash boundaries. That this is the minimum safe distance where we can locate to not get exposed directly and to not be affected to an arc flash. This distance, as you can see here, will change depending on the hazards that the potential arc flash will be. So it is not something that is standardized for all of the industries, depending on what is the voltage or what type of arc flash we may have. We need to define those boundaries. So at the beginning we have this arc flash boundary, that is the minimum distance, and basically is the distance at which we are safe from the exposed energized conductor or the circuit parts that are a potential source of this arc flash. When we move forwards to this energized conductor, you will find that you will find different regions, and the next region is this one, that is the limited space approach. And within this boundary, basically it is possible to be exposed to a shock, and also it is possible to be exposed to the arc flash, and in that case you have to already be wearing protective equipment, and you should for instance work with the gloves, and also you have to be a qualified worker to be at this distance of the exposed conductor or of the circuit part. Then we have another region that will be the restricted space, and this area is the closest you can get to the light or the exposed equipment. And in order to be there or even to pass this boundary, you must be already a qualified worker with the proper training and with the proper equipment to get this close to work there. If you need to be to perform any work in the energized equipment, you also need to have a special permit and also special documentation that allows you and that qualifies you to do the work over here. But all of these areas have different requirements to be there, and they have to be delimited in the space physically also. Specifically in the context of high voltage systems, and specifically in the context of the batteries, the electrical fires can occur due to electrical faults in because of short circuit or because of thermal runaway in our batteries. And these are particularly dangerous in the electric vehicles, because we have high energy systems that are the batteries that are in place there. It means that we can release a lot of energy in those fires also. While the electrical fire are very serious hazard, they can be managed with proper design of the batteries, with training and with emergency protocols. So being prepared can save life and can minimize damages there. Some of the preventive measures that we can have in the case of electrical fires is, for instance, in the systems to have proper cooling systems, to have regular inspections of those systems, as well as, that is very important, to have the firefighting protocols that, of course, there are going to be everybody has to be training on how to work in case of a fire there. For high voltage fires, for instance, what we have to do is to use a large amount of water, and that is what is recommended to cool down the battery, for instance. And always use, if possible, the thermal imaging cameras to ensure that the fire is fully extinguished and that the battery is completely cool before leaving the scene and before assuming that it is already safe. And also, in case of fires, we also need to have emergency plans, and to have, if there is, for instance, this happening in a workspace, we have fire suppression systems, a clear exit near us and accessible to us, clear protocol for dealing with those battery fires, and trained people also to manage with all of those. And another possible or electrical hazard is going to be the short circuit. And when there is an unintended low resistance connection between 2 points in our electrical circuit, that will cause a short circuit, and this allows a massive amount of current to flow, and this can be overwhelming for the system, and also because of that there is going to be a fast generation of heat in our system. Some of the causes that may produce the short circuit are, for instance, having damaged insulators. If the insulator breaks down or it is broken a little bit, the live components and the conductors can come in contact, and that will create a fault and a short circuit. Then another probable cause of that is, for instance, having poorly connected circuits and poorly connected wires and terminals. Even having just a loose terminal can lead to the accidental contact between two contactors or two conductors. And finally, there are external factors that can come there. For instance, if we place one metallic tool in top of one of our connectors, that might create short circuit. Also, the breeze in general, moisture in the air, and so on. All of that can create direct paths of the current that will produce short circuits. In order to prevent all of those, there are many ways to avoid that. For instance, again, to have the inspections, visual inspections, that the cables are not damaged, that we don't have loose connections, and that we are wearing all the insulation that is required. Also, we need to have the proper standards for how to on what materials should be used, and at which distance the conductors should be to have a safety design. In the specific case of short circuits, one of our very good friends are, for instance, the fuses and the circuit breakers that we can see over here. And these are devices that can cut off the power automatically when there is a fault and when there is a high amount of current flowing through the circuit. This prevents overheat and will prevent more of the damages of the short circuit. And finally, another recommendation is to have the workspace very clean, to keep the work areas free from tools, and to avoid all of that, to avoid any accidental short circuits. Now let's take a look at the effects of these electrical hazards. And how do they affect the people, how do they affect the property, the environment, and so on. As we explained before, the electrical shock will have an immediate and very dangerous effect on the human body. This figure over here helps us detail what happens when the current flows through the body and how it will affect us. And also it will describe it will show us the relation and the effect that we will have in our body in relation to the intensity of the current and the duration of that current in our body. So as we mentioned, but just to make it very clear, at very low currents, you might only feel some tingling sensation, and that is something that is not very, very harmful. However, as the duration of that current increases, or the intensity of the current increases as well, it does more dangerous. So at moderate level, the shock becomes painful and your muscles starts to contract involuntary, and that is what happens in the section 3 of this figure. And if we go even beyond to section 4, when the current is very, very strong, your body response becomes life-threatening. And in that case, at this amount of current flowing, the shock can stop your heart, for instance. It can cause respiratory failure and even lead to death in some cases. Also, in all of those, the burns are often very common, and not just on the surface, but also in the deep tissues we may have some burns, as it will be explained in the next slide. Not only in all of the electrical hazard that we have defined, not only the internal system of our body gets affected, but also we can have visible and severe external injuries. The burns are one of those severe injuries that are the result of the electrical hazards, and they can vary significantly in the severity that we have. Here we are presenting the different degrees of burns that we may have in some electrical accidents. One example to make this very vivid, let's imagine that there is a high voltage arc flash, and this occurs near you and you are an unprotected worker. The intensity of the heat that is generated in an arc flash, and even if it is just a few milliseconds, can cause a 3rd or even 4 degrees burns, even without the direct contact that you had with the conductor that is carrying the current. Only by being close to an arc flash, you can be exposed to these severe injuries. And this is why using proper equipment such as flame-resistant clothing is so critical in some of the tasks that we have to perform. Besides of the short-term effects of the electrical hazard that we already discussed, we also have to be aware of the long-term effects that might affect our life. Some of those are stated here. First, we have the neurological damage. When we are in contact with severe electric shocks, for instance, the neurons can be damaged, and this can affect our neurological system in different ways. For instance, we may experience chronic pains, we can have tingling, permanent tingling, and we can have altered sensations in our body, as well as to have weakness in our muscles and paralysis, and even in some case we can have memory problems, difficulty concentration, and experience any other cognitive changes. Besides of this, that are physical damages, we can also experience psychological effects. For instance, having anxiety or post-traumatic stress disorders caused by the exposure to these accidents, and they can alter completely our life and our quality of life. After explaining all of that, now let's see how we can prevent all of that and what are the measurements that will create a safe environment when working with high voltage systems. That at the end is what is more important for all of us. Creating a safe workspace is not just about having the right tools, it is about also creating our culture of safety. This means that clear procedures, to having proper trainings, and to also have a well-organized workspace are the best defenses that we can have against the electrical hazards, and in general against any hazard. Nevertheless, here there are the 3 safety guidelines for working with high voltage, and this is just the top 3. There are many more, and that we will see later on, but it is just a quick summary of that. The first one is then to always use high voltage insulated tools. These tools are specifically designed to protect the workers from accidental contact to live electrical components, and they are meant to protect us. So, for instance, we usually recognize because they have a red insulation in most of the parts, so there is the minimum exposure of metallic, metal and any conductive materials is protected in this type of tools. The second safety measurement that we can have in general is to have dedicated workspaces for high voltage and for electric vehicles repairs. Mixing the high voltage work with general mechanical repairs will only increase the risk of having contamination, of not using the right tools, and to expose, for instance, the people to flammable materials and so on. So to have this separated area would allow us to reduce the general risk in the workplace. And the last one is to have all the markings in our workspace with clear signals and with clear warnings. And all of this means, for instance, having the use or to use these black and yellow tapes that are used to designate different areas, for instance, to designate the high voltage system areas and where we take repairs there, and also to have some visual and auditive alerts of when there is a potential hazard, and how to keep people at a safe distance of the different work that we may be performing. Building here, or maybe to building on the importance of the workspace safety, I want to show you here some of the electrical safety measurements that we have to always use, and that will allow us to prevent all of the hazards that were explained, like electric shock, arc flash, and burns, and so on. One of the simple yet the most effective safety measure that we can have is to always use this isolated footwear and also isolated gloves. That creates a physical barrier between our body and the circuit, and also prevents the flow of current in case of any accidental touch with live components. The second one is going to be to use the fuses, the circuit breakers, and different components that are going to be the first line that we have to defend ourselves in the case of short circuits, and in the case of electric overloads in the systems that we are working there. These devices will work automatically, cutting off the power in case of any faults, and it reduces severely the risk of having overheating, fires, and also having the effects of those short circuits, for instance. The next one is then the electrical earthing. This will be explained later on in detail, but this basically includes or means that we will create a direct path, or we will avoid the direct path of the currents to go through our body, but we will force them to go through a safety or to go safely in the direction of the ground, and to prevent them to pass through our body there. And the final one is, as was mentioning, to use specialized high voltage tools to protect both the workers, but also to protect the people that is around us. One general and practical tip is that when we are working with electrical systems, even if they are high voltage or low voltage, we always have to treat equipment as it is live until it is proven otherwise. Never assume that a system, that a socket, or that a battery is not energized unless you have personally verified and you have used the appropriate testing tools to verify that. That is a practical tip that we have to follow also. Another important preventive measure that we have to do or we have to work with is the workspace design and how we do the maintenance in that workspace. Some of the key elements we have are, for instance, the traffic routes, and to have in our workspace clear marked pathways for our workers and for the equipment is essential. To ensure that there is enough space for the worker to move safely, even in the case of emergency situations. Then we also have these safety signals, and this is going to be visual or auditory signals, such as, for instance, I don't know, warning lights or alarms that we have that will indicate us in the case that high voltage systems are being serviced, for instance, and in that way everybody around us is notified that they have to be aware of certain type of hazards that in that area. And the last one is to have then emergency exits, and those emergency exits must be easily accessible for everybody without obstructions all the time, and they have to be also clearly marked and as part of a evacuation plan that everyone has to be aware of. Another essential aspect for preventing the electrical hazard problems and the other type of problems that we will see later on is the safety training. No matter how advanced the tools are or the protocols are, to have those trainings is always effective to ensure that everyone understands and knows the protocols correctly. Safety training will equip the workers with the knowledge and with the tools to identify and to mitigate the risks in the environment that they are. And some of the key components of safety treatment is, for instance, to handle and to use safety instructions, to have clear, consistent instructions that are going to be tailored to a specific task in the workspace. That is very important. To have, for example, step-by-step guides on how to de-energize high voltage equipment and how to handle, for instance, thermal runaway incidents or fire incidents is going to be very important. And alongside with these safety trainings, we also have need to have refresher of those trainings, even annually or very often. And this is in order to keep the workers up to date with the latest standards, with the tools, with the best practices, and to refresh all of this knowledge that allow us to be with and to create good habits that only can be developed over time. Another thing or another key topic here is to have emergency responses protocols, as well as to have teach the people how to identify the risks. Finally, and just trying to conclude with this part, I want to show you here a very simple but also very effective measurement that you can already start using in our daily life, I will say. That is the hand in the pocket rule. This practice alone is not not sufficient to protect the people, but it will add an external layer of protection when we are working very near to an electrical component. And it basically says that when we are keeping one of our hands in our pocket or maybe behind our back, and when we are working near or close to an electrical equipment, having the hand in that location will reduce the risk of creating a path for the current to flow through our chest and finally to vital organs, for instance, to our heart. It is important to note that this rule is not the substitute for all of the safety measures that we discussed before, like for instance wearing the insulated clothes and to using the insulated tools, as well as following the procedures and so on. This is only another measure that we can take to protect ourselves even further. Finally, this is another topic that is very important, and I would like to explain it a little bit in more in depth. That is the electrical earthing. So the electrical earthing at the end is the process that we have of transferring a high amount of current directly through the earth or send it to the earth by means of a low resistance wire that is physically connected to the earth. And this creates a safe path for these fault currents or for all of these hazards that we may have, because it prevents them and prevents that current to flow through the equipment or to flow through the people. To exemplify that a bit better, let's imagine that there is a worker and this worker accidentally touches a live wire, for instance, accidentally touches this electrical equipment over here. Without having the proper earthing, what will happen is that the current will travel through the body of this worker, and it will create at the end the shortest path to go to the earth will be the body of this person, and this will cause severe electric shock and maybe all of the possible effects on this person that we already discussed. If the same people or is the same person touch the electrical equipment and this equipment has already earthing, a good earth connection, what happens is that the current will safely flow through the grounding system and will protect the worker at the end. So earthing is not just a technical requirement and a safety requirement that we have. At the end, it is a safety system that will protect the equipment and will also protect the people that is handling and the user, and it is mandatory for the systems to have measurements like this one to protect the people efficiently. To conclude here, I just want maybe to conclude with a message that safety is a shared responsibility, and safety, it is not just about protecting yourself, but also is about how you can protect your colleagues, how you can protect equipment, and how you protect in general the environment where we are. So it is not all of the measurements that we have seen here have to foster a culture of safety that must to be a shared responsibility between the different work teams that are handling these issues together.